Mr. Christian,
Hello again, Mr. David.
how are you?
Good. Happy New Year.
Happy New Year. Been a long while. Been a long while. I haven't sent that.
How is Canada?
So far, it's a little bit cold. So as you can see by my hoodie, my toque. So I hear that Jax has some new Christmas gift for this new year. We're going to talk about this new cool API.
Yeah, sadly we couldn't do it on December. I guess.
We did a little bit on the last few minutes
Y-
of the first one.
yeah, but we kind of hinted that we were gonna do this episode like a long time ago, but then we had some.
Clio appear. So for those who don't know and want to see it, please take a look at the Christian Garcia channel. We had a video about like loop utility developed by Christian to do like learning. Oh yeah, I think that this was due eventually.
Yeah, so I wanted to cover the Flax APIs for parallelism because we already sort of did parallelism exploring JAX.array, but we sort of did it in a, let's say,
Featured
very,
way.
yeah, we did it in a very hacky way or very not so general.
Hmm,
But recently there is a new guide. Let me gonna share my screen.
yeah.
There is a new guide for should see close this. There is a new guide in Flax for that shows how to scale up models using a Pidget,
Hmm.
and it shows two new APIs, which I think is what we're going to see today. And
Uh, this is really cool because I think that the only reference that I could find when I was doing like parallel was a talk from Matthew Johnson that he was talking about like experimental PGIT and that you can how you can create mesh and everything. And that was it was not at the GTC, it was like I think at the Harvard machine learning meetup. And yeah, this seems I don't know, but sometimes JAX and Flax seems that they have very good stuff, but very not well documented features. So hopefully this will help eventually.
okay, now everything we're gonna do today is documented, and um, it's going to be. I think we're gonna see a more streamlined, uh, some more streamlined code. So what I'm gonna do is that I'm gonna copy our getting started with Flax, and I'm just going to rename it uh, Parallelism with Flax. Parallelism with Flax, which is today's topic. Uh, let's update the episode. Uh, okay, yeah, C code is not here, so uh, and this is not a real notebook. I'm gonna pass this here, and this is also not real.
Mhm.
Uh, okay, yeah, so we skipped an episode. So my idea for today, Mr. David, was to
Mm.
uh,
Would you mind if you can close if you can
sure.
close the thing? And let us augment a little bit the font size. Perfect.
Okay.
Yeah.
Yeah,
Good.
so my idea is to get the Flax code we got from the Flax episode,
Mm.
and then show how to use some of the new APIs to scale up in a mesh in a TPU,
Mm.
scale up to multiple devices. So okay, just a refresher of what we had. We basically had like the MNIST, and we were basically had like the simplest classifier, which is just kind of a linear function here. And but we had to change this a little bit. Uh, but what we had was basically like a training loop, maybe down here. Yeah, we had like a basic training loop. And we're gonna see how much we have to modify
Mm.
to get it running with
So
basically the new JAX.array APIs plus the new Flax APIs, which we will see in a bit.
yeah, so just to recap, so we have the model, simple multi-layer perceptron, and can we take a look? And you have the code for reinitializing the state. That's about it, right?
Yeah, I think we we can do things a little bit different. So let's here just create the module. Let's change the code a bit. So let's sort of refactor it. Let's construct the model here.
Mm.
Just so we see uh, because here we're kind of learning and seeing what's happened, but we don't need that. So let's just fuse these two, and we don't need this one. We can actually just do this one here. So okay, here we're just
That's so
create.
that's really cool of Flax that you can get this kind of table information with parameters.
So in this cell, we're just defining the model and sort of viewing it.
Mm.
And I hope it might break. There might be a bug, but let's see what happens. And here we are initializing the state.
Mhm.
And yeah, maybe we can keep this because I want to show some things that happen here. So okay, what's the idea? We we're going to use a okay, so maybe I have to copy some code. We're going to, apart from this, define like a mesh.
Yeah. So
And
before into that, so could you define what is the purpose of a device mesh of a physical mesh?
yeah, maybe let me just copy this,
Mm-hmm.
uh, which is the code I was experimenting on. Uh, and maybe we can define the mesh after the data.
Mm.
So, okay, we're using the new JAX dot sharding module. Well, I think a lot of these already existed, but they were
Yeah, under the experimental JAX.experimental API.
so they're moved here. And what we're going to do, if we remember the first episode we saw, uh, we we are going to create a mesh with some named axes. So the shape of the mesh will be we on the TPU that I have here. We have 8 devices. And for we can play around with this, but for our simple experiment, we are just going to have them in a like a linear uh, well it's not even a grid, it's just kind of a linear layout.
Yeah.
uh, and uh, we're going to name that axis data. So we're going to create a like a single axis where we have all the 8 devices, and that will be the configuration of the mesh.
So just a few questions. So So a mesh is a device mesh. It can be anything, GPU, CPU, GPUs. Is there any constraint when you're defining the mesh?
I don't think so. Like usually you have your devices, and well, they I guess depend on what JAX can uh, have access to, which is usually either TPU or GPU,
Mm,
and once you have these devices, uh, you can construct a mesh, but this mesh is more of a logical thing than a obviously they can be in a mesh, in a physical mesh,
mm,
which on TPUs they have a specific layout, which I think we were told that these create mesh functions try to optimize the layout
mm.
such that it's optimal according to the
Topology
physical.
of, yeah,
Yeah. But we already covered this, so maybe let's skip a little bit over this.
right.
Um, with this mesh, taking into account this mesh, we're going to basically try to partition our model accordingly. So, okay, what will happen in our actual model? So previously, we basically tried to only replicate our model entirely. Like so we're going to do only data parallel.
So wait,
Eh,
we're going to do so in the many devices. We're going to have a copy of the models, or it's just one model. It's one model, multiple data, or multiple data.
so what we want to do is for data we want to basically partition.
Mm-hmm,
We want to partition the data on the batch axis. So we send a different copy to a different device. Let's start with that
mm-hmm.
uh, because that is easy and works. And later we will partition these on the features axis. So we basically the kernel of the well we only have a single linear layer. We will partition the kernel um,
So
in such
the weights and bias parameters are in each device, right? Seems so.
uh, on the first iteration, yeah, we will just replicate them, but then we will partition them such that a subset of the weights live in different devices. So that is when you get model parallel and you can scale. I guess your model to bigger. You can get bigger models as you have more total memory.
Gotcha.
So that's what we're gonna do. Um, so first, let's start just with data parallel. So okay, we did this on the previous. So we did this at the end of one of the JAX of the Flax episode. Um so we are going to do it again, and here, okay, we actually have to from Func tools import partial. So we have to. So we're accepting like a module here. We have to uh, if static argnums 0 uh, and we just have to okay so this is just because module is static, so we have to use this decorator, missing a comma here. Okay, so here we're going to create our state, but we're going to create it partitioned. That is the goal. Okay, no, first we want to create it replicated. So we have to do a couple of things here, uh, there are some little tricks that we had to do. First thing I remember we had to do is that there will be some integers here or some like Python numbers. We have to convert everything to a JAX array. So we use tree map, and we use as array, as array and state. So okay, this was like a little edge case we had, and yeah, we're gonna return state, but now we need to replicate it. And previously we cheated and we just basically created like a partition spec that replicated the whole model.
Mm-hmm.
But here we're going to do something more generic. So uh, let's let's first start start with that. So let's just remember what we did previously, because we need the p object. So what we're going to do, let me skip to the part where we modify the model, is that here in the dense object, we're going to use some new APIs that tell Flax how to partition the parameters.
Okay.
So maybe we can define like the dense object here at the top, and uh, so okay, features. What we're going to do is that we're going to mess a little bit with the kernel initializer, but we're not going to use this one.
Mm-hmm.
And so I think the default one, if you define them yourself, is this is like biases are at zeros, and kernel is at uh, normal. So uh, what we are going to do is that we are going to wrap these in using like a decorator provided by Flax that lets us add some metadata that partitions uh, the weight. So uh, the API is with partitioning, and it accepts the regular initializer, and then it accepts the names. So
This is the
uh,
name of the batch access of the shared
yeah,
access.
yeah. So okay, for okay, this will be a little bit silly, but we're gonna start with just passing no names. This means
Mm-hmm.
we replicate everything. Uh, or if we want to be a little explicit, we could say none. Let's do that so it looks less silly. So yeah, we're gonna replicate all the kernel, and then maybe maybe let's just do the same here. Um, are there any questions in the chat?
No, yet I'm taking a look. No worries.
Okay, but here is zeros, and here we actually only have like a single dimension, so it would be none. This is very explicit. So okay, here we're just saying, and this goes back to the signature of the partition specs that we saw in another episode, fully replicated and fully replicated, and then we just call it normally. So this does some things in the background, but it doesn't impact the model initially. Um, the only thing is that if I run this, I think it's gonna crash. Yeah.
Can represent another.
So this is something that I am fixing in a PR because as let me just comment this and I can show you maybe in a different way. We changes for init and we see the variables. Let's visualize this. We'll see that we get some different things. So I don't know. Let's x.tree map. Let's get the shapes just to see what we have here. So but what we can see is that instead of having like just the parameters here,
Of a
we
partition.
we have some objects that are here. So we get this partitioned object, which is a pie tree, and it has the value, which the value is the actual array. Here we're viewing the shape. Normally we would see the array here, but we replace it for the shape, and we also have the names. Only problem is that the tabulate code currently crashes with this type of object.
Yeah,
But
we can
we
just
have this.
we're going to
So
put just an issue tracker to the developer that did this kind of tabular representation. Should take care of that.
okay, so yeah, I'm fixing that. So, but okay, the cool thing that we'll see is that this partition object is actually a pie tree,
Okay.
and it mixes with the next API that I'm going to show. So, first API is with partitioning. We add some metadata to the variables, to the parameters, and the next thing is that we can sort of retrieve that metadata. So what we can do is we can create like a state spec here. In the state spec, we can get it with get partition spec of the state. So now that we have these objects, we can get their partition specs, and this is just like the same type as the state, but it has these partition spec objects, which are, I think they're these p objects.
Just the realization of a partition spec.
Yeah, because here we only have the names, and when we do this, we get the partition specs applied. So we have the spec, and what we are going to do here in line is that we are going to apply this to the state. So we already did this previously. We're going to apply some constraints. So we're going to apply with sharding constraints, and this is what we're going to get finally. So the trick is metadata is added to the state. We can, using that metadata, construct the partition specs, and then with that we can constrain the spec.
In where I have a question, in where we added the, so when we created the mesh, it was saved So where does JAX have this information of the physical mesh that we write? Because
Okay, yeah, that is something that I'll show you in a bit.
okay, sorry.
Uh, no, that is a good question. Currently, it doesn't. If we see code that we had in other places,
Mm-hmm.
we had to create a mesh, and we had to pass the mesh and the partition spec.
Mm.
We're gonna use a different API, which is that we are actually going to do this. So we're going to uh, use, so this is a trick that is covered in the PGIT guide from Flax. You can say with a mesh. So you use a
Okay.
context manager, and that takes it into account when you're going to do this type of operations. You sort of pass the mesh to everything, so you don't have to specify hard code it here. It's
Okay.
kind of a trick, which is very useful.
Mm.
So yeah, that's a good question. The answer is this.
Context.
Uh, so okay, let's see what we get.
Mm-hmm.
Let's run this. Let's create it, and let's see what happens. Uh, okay, it worked really quickly. Uh, so actually, we're not gonna see anything different. We already saw this, except that it worked. We have our partition things all over. The important thing that we have to maybe test out is maybe uh, like as a sanity check. Let's visualize the uh, visualize the array sharding
Mm-hmm.
for an array. Okay, yeah, thanks. Uh, so we can view for the dense layer the kernel, the partitions. So okay, something
Partitioned object has no attribute shape.
shape. Okay, yeah, this is correct. Uh, we have to view the value. Uh, value. Yeah. Okay.
Cool.
So actually, this shows that we failed. So okay, no, this is correct.
It's all
We
replicated in all of them. That's what we
it's
wanted.
replicated in all of them. This is good.
Mm.
Just to show like what happens if we remove the constraints here and we run everything, we should get like
Only one device. Ah no.
okay, no, it's still putting in all of them. Um, let's see, it's because we're applying the mesh, maybe, or
In the device, when you define the module, you define that it's partitioned. So
let me see. It could also be because of this code.
yeah. Mm.
Let's try a couple of things. Oh, okay, no, if we remove this code, yeah, it definitely
Mm.
won't work. Uh, let me just try something out. Uh, what if we do it without the mesh? Uh,
Yeah, one device.
user. Yeah. So without the mesh, things are only one device. If we add the mesh back, things are replicated. Oh no. Okay. Okay. No. It's. I think I just didn't save. So
Yeah, it looks like we assume that when we change the state. Yeah. So yeah, makes sense.
should be this. And we're back to replication. Yeah,
Mm-hmm.
I know something funny happened, but uh,
The dangers of Jupyter notebooks when you don't run the previous cell.
yeah,
Just
without this, you're not doing anything. You're not replicating. Basically, you just put them in where the default device, which is CPU 0 here. We're applying them, so we get them in replicating all the TPUs. And okay, to finish the examples. Okay, the beauty is that okay, we can try. Let's try minimal changes, and then we do maybe some optimizations. Uh, okay, here we had our super simple training loop. The only thing we have to do is that we have to like replicate our data. Uh, we we can do this in a couple of ways. Um, what would be the most optimal? I am guessing.
beam up lambda x, something like that.
let-
My
Let's
guess.
let's try. Let's try some weird stuff. Can we? I'm not sure this is optimal. It
Mm-hmm.
might be. Let's try to do it here. So let's try to replicate the data here because we have the batch. Uh, just 1 second. Sorry.
Mm-hmm.
Uh, just 1 second.
But yeah, so something something that is always or when I learned parallelism in JAX and Flax was that you always have this kind of P map and then you have Pidget. And one of the funny things.
Sorry, I have something urgent on the door. Just a second.
All right. Yeah. So funny thing is that so when these features were shown, I recall that I saw a Matty Johnson talk in which he showed PMAP and Pidget, and one of the few examples that he tried to develop, or at least tried to show, was that with Pidget you can let the compiler take the wheel. And when you let the compiler take the wheel, he was showing that he can do like this kind of awesome parallel stuff, model parallelism. Even if you were doing like convolutional parallelism, like you can do also convolutional space parallelism, and it was a very convoluted code, but it was really really awesome to see that it can be done. But yeah, with this API, as you can see, we make very few changes. I know we have talked about a lot, but we haven't done many much changes, and you have this kind of parallelism for free. More
Okay.
parallelism, and then we're going to do like what we're going to do right now, which is data parallelism.
Okay. Sorry.
Mm-hmm.
So what we are going to do here is that we're going to do something similar to what we did above, but we're going to try to do it here for the batch. So we're going to apply some constraints. Uh, with starting constraints. So we have the batch, and what do we want? So we're going to use the P object, and it's going to look very simple. It's just going to be on the data. So the first dimension, we're going to shard the data on, okay, a little bit redundant, on the data dimension. So this piece is partition spec, which is just the tuple. So
So
yeah,
the name access, the argument for when you create a partition, the second name argument is the axis name, and then you give it the name of the axis, right? To much better identify, I guess.
we're gonna say that the axis 0, it's going to be sharded in the data dimension.
Makes sense.
of the devices. So this gives us a data parallel, and that should be enough, with the caveat that uh, we probably have to add like with mesh here. Uh, we have to add the context manager, so
Mhm.
so it replicates. At the end, I might try to simplify this. I want to create something
Now
s-
let's take a look. Mhm.
slightly different, but this let's try it out. This should be enough. Let's see. Okay, yeah, we didn't get any errors, which is nice. I hope this is doing what we think it's doing. So that's one of the tricky things with Pidgit. Everything is too magical, and then I guess you have to do some sort of inspection, or you're not.
Is
Yeah,
that it's very difficult if we like try to do like if we benchmark the model running on one device and seeing that we actually getting the theoretical speed of adding 8 devices.
yeah, we can try. If we make the model a bit more complex, we can add like an intermediate layer that it's a little bit. Uh,
Yeah, because with the small object, I guess that you pay more for creating the whole thing for making parallel, and you will not see the performance jump, right?
uh, yeah, here, well, things are a little bit meaningless because we're doing a data parallel training, but it's a very small model. But I mean, we're just doing this like as a sanity check.
Makes sense.
The next part is where we. Okay, so we did data parallel. I guess the next step is, let's try to do model parallel. And for model parallel, we have a little problem, and is that we need the. Okay, so when we partition, we need to make sure that the array, or the dimension of the array we're partitioning, can be divided on the uh, size of the dimension. The problem with this is that if we do something like this, big data, so this is ideally what we want to do. And okay, this is a very simple form of model parallelism,
Hmm.
which is just reusing the data parallel dimension. Uh, we can maybe in the next episode view what is actually shown in the guide, which is doing having a data dimension and a model dimension. For now, we're just gonna have split the model in the data dimension. The only problem is that we cannot really do this because here we have a 10. Um, we're I mean, we're classifying the number of classes is 10. So and 10 is not, you cannot divide 10 by 8. So
Not in my
so
book.
so what we probably have to do is maybe create like a we have to create just to showcase what we want to do. We have to add another layer that can actually be partitioned, which I guess the head you can just replicate it, so that is fine. uh, so let's just do something like this. I guess we add like a redo here. uh, which and then we have the actual head. So let's copy this. Uh, let's actually add, yeah, a single layer. So it's no longer linear, but this will be replicated as we will see.
Mm.
But this one, let's put some number of classes that we can actually partition. So let's put something like 64. Uh, and okay, now that we put 64, we can actually partition it because it's divisible by 8. And let's, I don't know, call this hidden, something like that. Uh, and things will not crash. So, okay, what happened? We missed something. Okay, we have to put here X. Uh, okay, yeah, now we have two layers, but one is not partitioned. The head is not partitioned, and the hidden is partitioned. We can even put it a name, like name equals hidden, just so we can see. And here name equals head. Um, okay, so head not partitioned, hidden partitioned, um, and we're partitioning the data dimension. So yeah, I guess the rest should work. I'm gonna explain
Exactly.
something in a bit,
Mm.
but okay, here it's gonna crash. So okay, here we can take a look at what is happening. So head should be replicated. Uh, okay, head actually doesn't have this partition, so it should be replicated. And then hidden uh, is partitioned and should be okay. We get it. Hidden is sharded, so it's cool. And okay, the rest should be a little bit magic. Uh, should be slower, possibly slower, because we're doing very like a lot of unnecessary stuff. Uh, but it should be training. So okay, it is training. I wonder if
Cool.
it converges faster. One thing we could try is we could try to stress, like have a hidden dimension that is so big that it doesn't fit on one machine, uh, such that we would we would need the model parallelism,
Mm.
uh, depending on, so if we have extra time.
We
uh,
have 20 minutes, I guess. Or we can leave it for the next episode.
yeah, let's see where we get. uh, yep, okay,
Cool. Yeah,
train
makes sense.
train trained as expected. uh,
Mm.
Probably since we have a hidden layer, it got a little better accuracy. So what we would probably want to do is let's um, let's maybe try. I wonder what would be big things that so we're fully replicating it. I wonder what would be like big for this, like 10,000, 100,000. Is 100,000
enough?
enough? I guess we can see just by running this one if it. Okay, so this one is actually not replicating it. Yeah, here it's all of these variables which we should free these variables. Uh, but this is good for now. Let's put a number here that crashes this. We should get like an out of memory, hopefully. Uh,
Nope.
nope.
I think it would be much better if we do 1e to the. Oh, there you go.
Okay. So it seems that yeah, we cannot put these on
Single device.
single device. One thing we should do here very quickly is to del the variables. We should free space. Yeah, let's free this, and let's okay, we should be able to run this and verify that we don't have space. So yeah, we don't have space. These variables don't exist. Let's verify that they don't exist. Variables, they don't exist. And we could not fit this. So we have a problem.
Why?
Okay, no, this is not what we want to test. So
Why not?
uh, let's just verify because what we want to try to basically, let's copy this here. We are missing the state of the optimizer. So let's try to do this here and okay, we could not feed it unreplicated. Let's see if partitioned. Now we can feed it. But let's view this for a smaller number just in case. The optimizer takes like a lot of space. Okay, no, could we could fit this one. So this one we can't. I'm just going to restart everything. uh, so this one, now that okay, we need to partition it. We couldn't fit it last time, but this time it should fit. It didn't fit. Let's see, data here.
Nope.
Okay. Let's. So it doesn't fit here. Let's try it again. It fits. Okay, this one fits. It's just
Replicated. I don't know why it doesn't show the TPU's names anymore.
yeah, it's not showing the TPU names, but um, just as a sanity check, head. Okay, yeah, it is partitioned.
Mhm.
Now we have to see. We have to find a magic number here, such that replicated doesn't fit. Let's see if
You want to do binary search? So let us take with the
we have to do
5,000.
a bit of a binary search here. Let's restart the notebook. Eh, Okay, okay. So, okay, 1,000 does fit. Let's see, 5,000.
You started? Why?
Oh, this one fits replicated. We have to find one that doesn't fit replicated. Okay,
Resource exhausted.
so data. Uh, let's restart. Let's see what happens. Oh, still no. Uh, okay, so too
Exhausted.
much. Mm,
2,500,000.
yeah. So let's try 250. Okay, this fits like this.
3,000,000.
No, it fits. Now, what we would like is that it doesn't fit like this.
Sorry, yeah.
So we restart.
I think that next to the play, you can actually let them run and above, run above, next to the play button on VS Code.
Okay,
Exhausted.
we got the number, right?
Hmm.
Okay, so 2,500 doesn't fit unpartitioned. Let's just do it again. If we don't partition it, it doesn't fit, but if we partition it, it does. Um, so this is kind of what we were hoping for. Uh, so okay, data. Let's restart, clear all, and okay, let's hope this works. So yeah, here we're finally for a very toy problem. Using the actual partition. I actually don't know if this will run because we fit the parameters, but
We didn't fit the optimizer.
I mean we when you actually run it, you have to save space for the gradients and a lot of the forward computation. So This we might get an out of memory down here, but this was just to show like, okay, we partitioned and it actually has like an impact. Uh, so yeah, okay, we got the out of memory. Let's reduce it a little bit
To
until we
two
get.
million 350K.
Yeah, it's that this number is a little bit crazy. Let's just go like for.
No, but the 1,500,000, I think we made it work. I think
I'm not sure.
two
I'm not
million.
sure.
Like if it's imagine that each parameter is around what, less than a kilo. I think that 2 million will be fine.
2 million. I'm not sure. Let's just see what happens. But we got like at least. Okay, yeah, it's training. It will be super slow. Uh, mm, okay, was compiling. Yeah. Okay, it won't be that slow after it compiled. Uh, so, something that I wanted to show here. Um, Usually in Pidget, you you also have to constrain the output. That is something that you have there because we don't know. We hope that it inferred the correct spec for the output,
Mm.
but we don't actually know. So
But it wasn't on the when since Jack have access to the typing to the signature of the functional notation. Isn't that information that is available to XLA or?
no. So what is happening is that here we get some partitioning, but we don't have a partitioning for the output, and we don't know if it will pick the same one for the output. So to force it, we can use the trick we did previously. State spec equals get partition, and then okay, yeah, the same thing we had previously. So in pget you constrain it on the pget function here, because Flax has this get partition spec API, which is super convenient. We can do it in line, so it's kind of a Flax trick,
Mm.
which is really nice. Other frameworks, I'm not sure, they might have to implement something like this, but currently there's not like a JAX API for this, but this Flax API is good for this, and this way we know that the 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 output will be partitioned the same as the input.
Okay.
Uh, so that is one thing. While this trains, okay, it's gonna finish very soon. Uh,
So will be a huge parameter space for just the MNIST.
yeah, okay, we're super solving the ending. Okay, we got incredible. Our loss is really low, which okay, nice. I guess. Um, okay, one thing I wanted to do, just kind of as a helper, I wanted to do like I wanted to create like a decorator here,
Yeah.
like dev with mesh, and do something like this uh, with mesh. I don't know. I have to create like a dev wrapper. XK works, yeah, exactly. So I want to create like a decorator that uh, basically does the with mesh for the function. So we could so instead of doing this like this,
Mm.
we can do something like with
Much.
mesh. Okay, just with mesh.
Mm.
Uh, and then we don't actually have to do this. Uh, I don't know. It's kind of a something I
Syntactic
wanted.
sugar, syntactic sugar for the machine learning developer.
Yeah, maybe you can generalize this with actually passing the mesh here with a partial, but now we can run the function normally, and we can also do it here for our train step, and we can remove this. Um, so a little bit of
Mm.
here, just seeing that it works. But yeah, it looks a little bit better. So you can just do this with your regular training loop if you have this decorator.
But that's cool. Look, we just made a few changes on the model. We helped, on the model we define where actually is the chain operating. Also, if you want to have data parallelism, where we are going to have the data annotation. It was cool because it's minimal. I mean, doesn't it looks minimal, but like it looks that you just need to help the developer just where you want to shard, depending on the topology on that, and you have parallelism for free.
Yeah, yeah, so these are kind of the Flax APIs. We what we're doing in like the literature by partitioning the kernel on the data dimension. This is called the well on the zero papers. Okay, so we're doing two things or three things that but we get all of them for free. We are partitioning our if we see we're partitioning our parameters on the data dimension, but because this is a pi tree and optax operates over pi trees,
Mm,
we can see that the optimizer state is also partitioning the variables of the optimizer. So this is really cool that you get it for free. Here we're partitioning the Adam uh, like parameters in the same way as the network's parameters. So uh, this is really cool. So we are partitioning the data. We're partitioning the model. We're partitioning the optimizer. Even though okay, we got that for free. Only thing we could try to do to help it a little bit more is try to partition the gradients in the same way.
mm.
So
This doesn't occur like in differential uh, privacy gradient, something like that. That you do like gradients per example.
no, this is different. We just want to constrain it with the same constraints as the state.
Okay.
As yeah, so these gradients have the same shape as the parameters, and we might just to make sure that the gradients are also sharded and the XLA is not doing funny stuff.
Mm,
We can try to do something like this. So we can say, okay, so we get the spec here, and we do it at the beginning, and we sort of reuse it. So we want to say that the gradients are partitioned in the same way as the parameters. So this is more of a uh, just in case you want to make sure that everything is according to how you think it's going to do it. I think XLA would have done it anyway, or else it would be like super expensive.
Mm.
But you can try to do this, and if you partition your state, your optimizer, and your gradients in the zero paper, this is called the 03. That I mean, that's kind of the. So I think 01 is only the weights, 02 is maybe the gradients, and then 03 is also the optimizer, something like that. I don't know.
Mm.
Some combination of those. But in I guess in the JAX world is really simple. Just putting some constraints, and then the useful thing is having APIs to put those constraints easily. So JAX Flax's get partition spec thing makes it almost like trivial. And yeah, so well, we noticed that we didn't actually have to do either this or this, and it ran fine. This just sanity checks you can do to,
To
or
make sure. Mm.
yeah, to make sure, or if you're getting funny stuff, mm, try to help the compiler. And I think this is it. We can probably, so it's compiling again. We can probably end here. And
That would be it.
yep.
That was cool. Oh.
So yeah, maybe we can explore more complicated partitioning techniques. The Flax guide.
Mm. I think
Should,
that we should look for the other episode, like something like that, something like we can do parts from the zero paper and then follow this guide.
so that's kind of what I did
Mm.
personally. We can maybe take a look at their specific mesh. It's a little bit more optimized to how the TPU mesh is actually structured. So they create a 2 by 4 um, mesh. Yeah, they create like a 2 by 4 mesh, and then they do data and model parallelism. I mean, we could easily try it right now, but I think we're out of time.
Yeah, because it's 1 hour 10, and last time we we ended up 1 hour 30, and nobody was was I think at that moment.
Okay, yeah,
Mm.
I will commit this, and yeah, I don't know. Maybe next time we can continue with this, or we can just look at another thing. I found a like a, a guide for XMap.
The new, yeah, that experimental parallel named axis for parallelism, something like that.
Yeah, I haven't played with that, or we can try to do manual parallelism with PMAP. That could be
Mm.
like another topic. So all of this is automatic parallelism, which is very magical because we have to do very few things. Uh, I mean, we have to do things, but we have to
Mhm.
think a lot less of the details.
Mm.
If you do it manually with PMAP, that is another interesting topic because you have to think a little bit in terms of like all gathers,
All these synchronization methods.
Yeah, like average reductions or um, the different MPI style um operations that you can do. We can maybe play with that, but for now, I think we can leave it here, and yeah, we can continue our journey.
That was good. That was cool.
Okay, Mr. David.
Thanks. Then, Mr. Christian. So hopefully we'll have the next session in a few days. I was thinking, yeah, we could. I don't know if we do it the XMAP or we just can. We can always just continue seeing, looking at the guide.
Yeah,
Hmm.
maybe my idea is to do this like weekly.
Streamly Tuesdays.
Yeah, every Tuesday when we just see like what is up.
Hmm.
Can explore maybe simpler topics for people who are learning. That would be good. We started like with the heavy stuff,
Yeah,
but yeah,
that's yeah. I usually have that kind of thing that I saw with the heavy stuff, and then
yeah, we can use simpler stuff.
yeah. No, but that was good. That was good. I really like it. So thank you, Mr. Christian. So hopefully see you in the next time.
Okay, Mr. David. See you
Bye
then.
bye. Thanks for everyone.